Hello and welcome to Lecture 32. Here we're going to talk about calculating the moment of inertia as well as defining it, but the main actual computational focus is going to be how we calculate it, okay? All right, so the moment of inertia is basically rotational mass. It is what shows up in Newton's second law in rotational form. You'll see lots of applications of it in other lectures, but here we're really going to focus on how to deal with it, okay? All right, so first of all, there's going to be a useful theorem that we're going to use a couple times called the Parallax theorem. So let's go ahead and define that theorem under our key terms right here. So what the Parallax theorem is it's a formula used, okay, with axis of rotations that are not through the center of mass. Okay, so that's really its usefulness. It allows for easy calculation, it is quite easy to use, of moments of inertia about a new axis. So to kind of illustrate that idea, let's look at this figure over here. So imagine a cylinder, right? So we could have an axis of rotation through the center. Imagine it rotating like this, all right? And that would be passing through the center of mass, right? And that we call that the x-axis. So if we had that moment of inertia, maybe we calculated it or maybe we looked it up in a table. But regardless, the moment of inertia, the rotational mass of that cylinder is only then applicable to that axis because moments of inertia, just like everything in rotation, are specific to a specific axis. If we move the axis, then we have to change our values. It has a quantitative effect on the system. So for example, if we moved our axis over here to x prime, which is then touching the perimeter of the cylinder, that actually would change the moment of inertia. But we could deal with that change as long as we know the distance between the two axes. And the name, parallel axis, really shows up here in the picture because the x prime axis and the original x-axis, well, they're parallel to each other, right? Hence, parallel axis theorem. And all we need to know is the distance between them, h. Okay? All right, and we'll get to seeing it in formula form in just a second. So let's look at our key formulas. We've got 3 of them here. They all have to do with just defining the moment of inertia, rotational mass, okay? And moment of inertia always has units of kilogram meters squared. You can think of it having those units because it's mass times area. Whereas in translational systems, we only care about kilograms. We only care about the mass, the sluggishness of matter. But when we're rotating something, that effect of the sluggishness of matter, how hard it is to speed something up, slow it down, or to start it moving, or to stop it moving, well, it doesn't just matter how many kilograms there are. It also matters where those kilograms are located. What's the shape of the object? Which is why meters squared shows up in the actual units of the center of mass, right? Okay, so and then different shapes have different moments of inertia, okay? But all the same units, kilograms times meters squared. All right, but anyway, our first formula here is the moment of inertia for a system of discrete particles. So this is if we were summing up, particles relative to some axis of rotation, maybe they're all literally particles, or maybe we're summing up known moments of inertia, ones that we look up in a table, right? So maybe, we're summing up moments of inertia, but they're, one of them's a cylinder, one's a sphere, one's a rod, right? But maybe they're all rotating about the same axis. Or maybe they are literally just little point masses, okay? If they are point masses, then this formula would work perfectly. We have mass of particle I, and then we just simply multiply each of those masses by the position of particle I, and that is relative to some axis, right? And what axis? The axis of rotation, right? Because otherwise it has no significant meaning. We have to have it relative to something, and that distance r is measured relative to that axis of rotation. Okay, this is kind of similar to the center of mass formula, right? Where the mass and the location have an effect. The only difference here is that with the moment of inertia formula for discrete particles, it's the mass and the position have an effect, but the position is squared. And also we're not dividing by the total mass, right? Because after all, this is not the center of mass, but the similarity is definitely there. Okay, all right, well, the next formula is just the continuous summation, equivalent, right? We've just gone from a sum to an integral, and we've gone from basically a discrete mass to a mass element. All right, so this is for a solid object, a continuous object. So that's discrete versus continuous. Those are always, counterpoints when we're dealing with things mathematically or physically. Continuous objects, discrete system. Okay, but here this is for a continuous object. All right, so an infinite number of very, very small summations. And so this right here is the mass, but we call it a mass element, which just is to say this is an infinitesimally small piece of mass. Okay, the idea of the effect of the position squared is still there, but of course it's inside the integral, so we have to deal with it accordingly. Okay, and this is something we'll definitely be using, this formula, in the examples. Last of all is the key term. This is the parallax theorem. This is what it actually looks like. So if we want to find the moment of inertia about some other axis other than the axis that goes to the center of mass, then we just have to sum this second term here, which is the mass of the object This only works for solid objects, okay? I mean, I guess it could work for discrete particles, and in that case, your center of mass maybe would just be mh squared to begin with, or mr squared to begin with. But anyway, so here you would have the mass of the total object, and then this would just be the distance between the two axes, okay? So just like in the figure above, that's your h right there, and then the m would be the total mass of the cylinder, okay? All right, well, let's look at our practice problems. Although before we do, I actually have one last thing I want to say about the parallaxis theorem, which is easy to miss. You might think, oh, well, this just means you can move between any two axes, right? The idea is h is just the distance between the axes, right? Not so. One of the axes must be through the center of mass. The fact that this says I, is not insignificant. It literally has to be the moment of inertia as calculated about an axis that passes the center of mass. You can't just say I2 equals I1 plus mh squared, where neither I1 nor I2 are the moment of inertia as calculated about the center of mass of the solid object, okay? One of them, in fact this one, must be the one calculated about the center of mass, and that's an important distinction. That means that if you do want to go between two arbitrary axes, you have to go to the center of mass axis first, as an intermediate step, and then go over to the what would be the third axis, okay? And we'll see that. Okay, now the two types of problems that we're going to get practice with. Type 1, these are simpler ones. These are problems that involve finding the moment of inertia, starting with one or more objects of known moments of inertia that you would look up in a table about a certain axis, of course, and using the parallaxis theorem to move the axis of rotation. So there we're just using the parallaxis theorem and looking up common moments of inertia. Type 2 are problems that involve finding the moment of inertia of a continuous solid object using the density function of that object. Okay? Sometimes that density function is a constant, and every single time for type 2, we're going to be integrating. All right, so let's look at example 1, which is a type 1 problem. What is the moment of inertia of a uniform cylinder that is rotated about a point along its perimeter, such as when it's rolling? So that would actually, move up here, scroll up, that would be this picture right here. That would be a cylinder rotating about what I call the x prime axis in this figure, right? You can imagine it rolling, right? Okay, so, and then how would we do that? Well, to do that, we would then write that the moment of inertia about the perimeter is the moment of inertia about the center of mass plus mh squared. Here, I point out that the moment of inertia for a cylinder is 1/2 mr squared. Right? You can derive this yourself, or you can look it up in a table. All right? This is a very common moment of inertia for a uniform cylinder. Okay? So that means all I'm going to do is take that known moment of inertia, as from a table, plus mr squared, because here the distance h is the radius, because we're moving from the center to the edge. That is a distance of exactly 1 radius. Don't forget to square it. Then we get 3/2, plug in our numbers, and there we get our moment of inertia, okay? This is a much larger moment of inertia than the moment of inertia about the center, which is 1/2, right? Instead, it's 3/2. It's significantly larger, okay? Okay, now let's compare to a point that is halfway between its center and its perimeter. So that would be like a rotation axis that is like this, right? Right here, and rotating about that axis. So should we expect that to be larger or smaller than the answer we got for part A? Well, smaller, okay? Because it's easier to rotate it, all right? It won't be as small as rotating about its center, which is the easiest way to rotate a cylinder, but it shouldn't be as inertia significant as rotating it about its edge, all right? So as we see, and we see what happens, we take our moment of inertia about the center. In this case, h is 1/2 r, right, instead of r, and we square it, which means this becomes a 1/4 once this comes out of the square, and 1/2 plus 1/4 is 3/4, of course, and then we just plug in our numbers, and that gives us 0.375. So definitely smaller, all right? But not as small as if we just had the moment of inertia about the geometric center, which is also the center of mass, because this is a uniform density cylinder. Okay, all right. Let's do another similar problem, but with a little bit more steps to it. Here we have basically a dumbbell. All right. So determine the moment of inertia of a dumbbell shown in the figure and you got a few different axes we're going to do it. We're going to do it for the x-axis, we're going to do it for the y-axis and the z-axis, and last of all, for an axis that is parallel to the y-axis but runs through the center of the left sphere. Okay, so that then part D, it would be y prime. Okay, so we're going to do these 4 axes, and we're going to find the center of mass about every single one of them. Okay, so some things to consider is we have hy prime and hy. These are going to show up in parallaxis theorem calculations, because we're going to have to move from some center of mass axis, and that's the consideration we have to make. Okay. All right. So first of all, we're going to find the moment of inertia total of the object. Okay. And this would be about the x-axis, and it's always going to be the total because there's always going to be the sum of the objects. So let's think about what's going on here. Well, we'd have the moment of inertia of the rod, okay? And that would be, for the x-axis, that's going to be a rod along its line like this, okay? The rod has a diameter of 6 centimeters. It's the only value that's not shown here, because we see all the other values that are all along the x-axis are shown, right? But the diameter of the rod is not shown. It'd be this right here, all right? And that would be, the diameter of the rod would be this value right here, okay? So let's put in our appropriate formulas, okay? So the rod is a cylinder, so we'd have 1/2 mr squared, okay? Right, and r is obviously half of the diameter. And then we have the spheres. So we think about the spheres, what's going on with them? Well, both the spheres are along the x-axis, aren't they? So they'd have a moment of inertia, which would be exactly the moment of inertia of a sphere about its center, which is 2/5 mr squared. But there's two of them, right? So they contribute to a total moment of inertia. So it's 2 times 2/5 mr squared. And this 2/5 mr squared is the moment of inertia you'd see if you looked up the moment of inertia of a sphere in a table of common moments of inertia, okay? All right, so here we're just going to continue on with our values. All right, plug them all in, and here we get our answer, okay? The important thing is the form right there, okay? All right, and then in part B, okay, part B is the y-axis. Well, this is going to be different, right? Because the y-axis we have, the rod now is being rotated about center rather than treating it like a cylinder. Now we really treat it like a rod, because now we care about the mass that's distributed this way, right? Instead of the mass that's just distributed this way, right? So it's much more mass further away. So we expect this value to be quite a bit larger. Furthermore, when we're thinking about the spheres now are off center. So we have to use the parallax theorem, right? Because when we're considering the y-axis, each of these spheres is a distance hy, each of them, right? In magnitude at least, a distance hy away from our actual axis of rotation. So we see here that we have this effect of hy, making them effectively harder to rotate. And that makes sense because they're further away, right? But they're still spheres, so they still have that form, right? Which is the moment of inertia about the center. And there's two of them, so there's the two. All right, and then we'll just plug in all our values. And let's see what we get. We get 14, much, much bigger, dramatically bigger, right? Like, 2 orders of magnitude larger, right? Why is it so much bigger? Well, it's so much bigger because there's so much mass that much further away from the axis of rotation. It'd be much harder to spin the dumbbell that way than effectively to just roll it, okay? That makes sense. Finally, the z-axis is going to be exactly the same as the y-axis by symmetry. There's no difference between rotating it this way, right? So basically rotating it like that versus rotating it like this. They're exact, identical moments of inertia there. Rotational mass is the same along the x-axis or the y-axis and the z-axis. All right, so it's going to be 14 kilogram meter squared again. Now finally, let's deal with our y-prime axis. All right, so the idea there is we have the moment of inertia about the end of a rod, and these are common ones. The moment of inertia about its middle is 1/12 ml squared, the total length. The moment of inertia of a rod about its end is 1/3 ml squared. All right, notice it's L instead of radius because it's a different shaped object. It doesn't make sense to define a radius. So you see there's the 1/3 ml squared for the rod because again, it's about its end. Furthermore, we've got the sphere. One sphere is directly about its center, so that one is just a normal sphere. The other one we have to take into account the parallel axis theorem. That's this one here, and that's that much longer axis, hy prime. All right, and we plug in all our numbers, we get 28, the biggest one yet. So the most difficult way to rotate this dumbbell, I suppose even more difficult would be rotating it here, but rotating about the y prime axis is more difficult than any of the other 3 axes we've seen so far. Because there's more mass further away, thus making it harder to rotate. It would take more torque to achieve the same angular acceleration if you're rotating about this axis as opposed to the other ones. Okay? All right, hopefully that makes sense. Let's do a couple of concept questions before we get on to our big problems that involve integration. All right, so concept question 1. Rank from largest to smallest the moments of inertia I1, I2, and I3. Okay, so they're all essentially dumbbells, except the distance. The idea here is that the connecting rod isn't going to make an effect. To assume it's a massless connecting rod. Okay, all right. So we're only worried about the locations of m and the values of m, whether or not it's 2m, m, or m over 2. Okay, so the first one, the moment of inertia, is just going to be 2m times r squared. Okay, why is that? Well, because we're treating these like point masses. We're not treating them like spheres. We don't have to worry about that. We just care about the fact that the mass is out there. Okay. And again, you might be like, oh, would it be more accurate to treat them like spheres? Yes, but you'd still get the same ranking. So you might as well just treat them like point masses, all right? And the moment of inertia of a simple pendulum, of a point mass, as well as a hoop, because then the mass is all the way away, all the mass is distributed as far away from the axis of rotation as the radius allows. Well, in that case, any case like that, so this would be a point mass, any moment of inertia of that type of system is always just mr squared. In other words, the coefficient is 1. I bring that up because you notice that all moments of inertia have that form of some coefficient times mr squared or ml squared in the case of rods. And the idea then is that coefficient kind of tells you, like how hard is that shape to rotate compared to other common shapes. Well, the hardest shape to rotate is a point mass, like a tethered particle when all the mass is the maximum distance away. Okay, so anyway, so there's 2 of them, so it's 2 mr squared. All right, what about this case here? Well, we've reduced the radius. There's still point masses. One of them is bigger. So what do we get in that case? Well, we'd have 2mr r over 2 squared plus little m, or just a single m, times r over 2 squared, which then would actually just give us 3/4 mr squared. So even though there's more total mass here, there's a total of 3m, the fact that all the mass is closer, and the fact that the radius is squared, whereas the mass effect is not squared, means that even though this one has more mass, it actually has a smaller moment of inertia. And that just highlights the fact that the radius is so important for moment of inertia calculations. All right, and then finally the last one, well, this one, now we have that long radius, and I said radius is really important, so we should expect that even though this one is less mass, it actually ends up being a larger moment of inertia, right? See, because the distance is doubled and we're squaring it, which means we're picking up a 4 here, right? And even though the mass is cut in half, right, that 4 still gives us a bigger moment of inertia. In fact, twice as big as when there was twice as much mass, but the mass was half the distance away from the axis of rotation. This being, of course, the axis of rotation in each case. Okay, so that means we would rank them from, from largest to smallest. Well, it would be 3, 1, 2, right? Because 3 is the largest. Okay? All right, so let's do another one to highlight the importance of size and volume as well as radius for calculating moments of inertia. The idea here is we want to take a ratio of the moment of inertia of cylinder B as compared to the moment of inertia of cylinder A. I say they're both made out of aluminum. We don't care that they're aluminum. We just care that they're made out of the same substance and that they're solid. That way we can do a volume calculation. Okay? All right. So this is going to be interesting, right? Because how much bigger do you expect the moment of inertia of B to be? It's certainly going to be bigger, but how much bigger? Right? Is it twice as big? Right? Well, maybe, or is it like 4 times as big because because it's squared? Well, let's see. Okay? So first of all, the moment of inertia of A is just 1/2 mr squared. That's, again, the common formula for uniform cylinders. We're going to replace m, okay? We're replacing m with rho v. Rho is density, v is volume, okay? So then I'm just going to put in the form of volume for a cylinder. Well, volume of a cylinder is the area of a sphere times length. So it's pi r squared times L, okay? And then we still have r squared, all right? That's fine. All right, let's do the same thing for B. For B, I'm just going to skip right to this form here. And all I've done here is I put in the 1/2, okay, the 1/2. I've put in the rho, and then I put in the formula for the volume. But in this case, it would be pi times 2r squared, right, because the radius is twice as big, right, so that whole quantity is getting squared, and the length is twice as long, okay? Furthermore, the r that shows up in the moment of inertia formula, independent of the mass, right, which means independent of the volume, is 2r squared. Okay, so that means we have a lot of things squared, right? We're squaring a 2 here, we're squaring a 2 here. So it seems to be that this one's gonna have a much bigger moment of inertia. Let's go ahead and take the ratio. We'll cancel out all the like terms as I zoom in here. So the 1/2s cancel, the density of the aluminum cancels, pi obviously cancels. Of course, all the L's and R's cancel because they're all the same order, which means all the same dimension. And so what we're left with is 32, right? Where's 32 come from? Well, it comes from 4 times 2. So 16 times 2. So the moment of inertia of B is 32 times as large as the moment of inertia of A. I bet that's a bigger ratio than you expected. Again, just highlighting the importance of size and how the moment of inertia grows so rapidly in the case, especially when you take into account volume. Okay, now on to the problems that involve calculus. All right, so example 3. This is kind of a check to see if a common moment of inertia, actually, if we can derive it ourselves. So calculate the moment of inertia of a rod with uniform density that is free to rotate about a fixed axis through its center. Okay, so we want this axis of rotation, which is our, this is going to be our L over 2, right? So right through its geometric center, its uniform density. All right, so let's tackle it. Okay, so notice this term lambda. Well, lambda is a linear density. That's as in contrast to the value that we saw for density in the last question, which was rho. Rho is volumetric density. All right. There's also area density, and that shows up sometimes. We haven't seen it. We don't need it. So we'll just care about lambda and rho. All right. So that's kilograms per meter as opposed to rho, which is kilograms per cubic meter, of course. All right. And so let's go ahead and write out our moment of inertia. Okay. Oh, I have the word com there. That should not say we're not finding. Oh no, we are. Never mind. We are finding the moment of inertia about the center of mass. We're fine. All right. So there we go. Now that's the form. That just comes right out of the formula. Really, this is the definition of the moment of inertia. Right? It's an integral of the effects of mass, right, with the distance being squared. Okay. So now look at the way we're going to do our limits of integration. Again, because we're considering it about this axis right here. Right? We're calling this maybe y prime axis. If that's the case, then mass starts over here and it ends over there, which means it starts at negative L over 2 relative to our chosen axis of rotation, and it ends at L over 2. Okay. Now I don't have to do it that way. I could have calculated about y, all right, in which case my lower limit would be z and my upper limit would be L. But then I wouldn't be finding the moment of inertia about the center of mass, would I, for this uniform density rod? Instead, I'd be finding the moment of inertia about the end. So that would actually would have given me 1/3 ml squared, which is what you find in the table. Okay, but that's not what we were asked for. Now, but we could have done that. We could have found the moment of inertia about the end, found the 1/3 value, all right, 1/3 ml squared, and then use the parallaxis theorem to get over to the middle and to confirm that we were able to get there. Okay, but we don't have to, and that's the thing. The parallaxis theorem is always strictly optional. All right, especially when we're doing, starting from integration, because you can always choose limits of integration to avoid the parallaxis theorem. That said, sometimes it's easier, especially if non-uniform density, it's easier to calculate it about a easier axis to work with numerically and easier axis to keep track of some of the conceptual ideas, and then just use the parallaxis theorem afterwards. And we're going to see that in just a moment, okay? But here, I wanted to highlight they actually doing perhaps what would be considered the more difficult limits of integration, but again, doing it when we have a uniform density, okay? All right, so moving on. For uniform density, our linear density term, lambda, is just going to be m over L, okay? It's not a function of x, so we'll be able to come right out of the integral. It's a constant, okay? So then we're going to continue with our integral. We're going to, all I've done here is rewrite lambda as m over L. Otherwise, we've left everything the same because we already did our differential substitution, replacing dm, which is our mass element, because that we're integrating over, to something we can actually solve, which is lambda dx. And I hope that makes sense, that dm equals lambda dx. The idea there is that the mass element is some density times some infinitesimally short length. Okay, and that it matches that dimension and unit wise. So hopefully it seems fine. Okay, so we'll pull the constant out of the integral and also do the actual antiderivative. When we do the antiderivative of x squared, it's just going to be x cubed over 3. All right, and now we're going to concern ourselves with the evaluating the limits. So upper limit minus lower limit. Okay, so when we do upper limit minus lower limit, zoom in on this, right? So we plug in L over 2 for our x term. Remember to cube it, divide by 3, which came out of the rule for antiderivatives for polynomials. And then we do the same for the lower limit. Now what's cool about the lower limit is since it's a odd power, the negative is going to survive. The negative, in other words, the -1 would come right out of the integral as a -1. So then, so what we're going to have is then a negative minus a negative. So this is going to be a plus. All right, and then our L cubed is going to be over 24 now, because 2 cubed is 8. 8 times 3 is 24. So we have 24 in both of the denominators. So obviously these are like terms and they're adding together. And so then we get over 12. And then we cancel out one of the L's, right? This L cancels, right? And these both become 2's as shown here. All right, and so there we go. Last step, or the box, 1/12 ml squared, exactly what you'd find in the table for a uniform density rod rotated about its center. Wonderful. All right, we confirmed it, but then again, you're just going to look it up, right? Why do we have to confirm it? Well, what if it's not uniform density? Because then you're not going to find that in the table. You have to solve it yourself. Okay, so let's do an example that is not superfluous, but we actually have to do it ourselves. Let's consider a thin rod of mass m and length L that has a linear density that varies with length from some initial density, which we call lambda naught, on the left, so over here, to a density at the far end, so over here, that is twice as dense. Okay, and it changes, right? It varies linearly. Okay, all right. So we got linear density, and then we got a linearly increasing linear density function. I know it's a lot of linears in one expression, but the idea is it's just growing steadily. So the density is increasing steadily from one end to the other. All right. It's not like increasing as a square of the distance or anything. It's just it's a linear increase. All right. That's important. Okay, and then part A, what is the moment of inertia of the rod about an axis that passes through its left end, which is the y-axis as shown in the figure, right? And that's a good place to start because that's the easiest one to calculate. All right, so one thing we're going to have to consider when we actually do answer the question about an axis through its center of mass, which is part B, we're going to have to consider where that center of mass is, and it's at 5/9 L. I'll justify that we know that already, but in a minute. Okay. All right, so let's go ahead and start. So we're just going to start with the definition, okay? And again, it's just as simple as then saying that it's going to be, we have some mass element, we replace that mass element with a differential substitution, giving us lambda dx, okay? Notice our limits of integration here are going to be from 0 to L. Why is that? Well, because our pivot's at 0, all right? So then we're calculating it about that point. Now, again, you might be like, well, like the lower limit wasn't the pivot before. No, but the pivot was in the middle. Thus, we're integrating from negative L over 2 to L over 2, okay? But here we're integrating from 0 to L. So the important thing is your pivot point, your axis of rotation has to be at 0. It's just that now that's at the far end of the rod. So there's no mass past there, so we don't have to worry about integrating past there. Thus, we can start at 0, right? Which is nice, right? Because then we don't have, that means when we evaluate the lower limit, everything's going to become 0, okay? And now we'll plug in our actual form of our mass distribution, okay? And it's going to be just lambda times 1 plus x over L. Okay, so let's see. If I have, nah. Okay, so I was seeing if I had the step. So I want to show real briefly where that comes from. So if we consider a axis, which is lambda, so linear density, units of kilograms per meter, graphed against x, then there's 2 points that we know, right? We know at 0 at the origin, the value is lambda naught. And we know at x equals L, the value is 2 lambda naught. And then we know it's a linear value between the two, right? There's a linear function that connects the two. Well, that's enough information to find the equation of a line, right? Y equals mx plus b would become lambda equals, well, rise over run would be, well, there's just lambda over x, or lambda over L, right? That's because the rise was only a single lambda, because it was 2 lambda naught minus lambda, right? And it'd be actually lambda naught over L, and then times x, and then plus b, what's the intercept? Well, the intercept is, well, lambda naught, right? See it? And so then that means that our function, once we factor out a lambda naught, is just going to be x over L plus 1. See? So just from the equation of a line, also known as the point-intercept method of finding the equation of a line, we get that this is our lambda function. See it? Okay. So that's where that information comes from, okay? So we've replaced lambda with the actual function, which is a function of x. And that's very different than up before, where lambda was just a constant. It was just m over L, and we're just able to pull it out. Notice that m hasn't shown up yet. We'll get back to that idea, okay? All right, one thing we can pull out of the integral is lambda itself, all right? And then we can do the rules of antiderivatives, because we've got a couple of polynomials. We've got, once we distribute the x squared, we have an x squared term, which just becomes x cubed over 3. When we just distribute the x squared over here, we have x to the 4th over L, which then becomes x to the 4th over 4L. All right, limits of integration that we're going to evaluate are going to be L and 0. All right, so we evaluate the upper limit and the lower limit. Lower limit just gives us all zeros because everything has an x in it. So we only really care about the upper limit. We plug it in, we got our L cubed, and we got our L to the 4th. Right away, one of our L's cancels out, so we're just left with a 3 there. All right, so which means these are going to be like terms. We're going to have a third plus a fourth. All right, so a third plus a fourth is 7/12. All right, and you can check that in your calculator, but a third plus a fourth is 7/12. Okay, and we have L cubed, and we got a lambda naught. Okay, does that mean we're done? Well, no, not at all, because this is not the correct form for the moment of inertia. All moments of inertia are always going to be, some value, we'll call it beta, and then, times m times L squared, or maybe beta times m times r squared, depending on what kind of object it is. But there's got to be some number, right? Beta is a number, like 1/2 for a cylinder, or 2/3 for a spherical shell, whatever it may be, right? It's just some number. All right, but here we don't have that, right? We got the wrong order on our length, right? It's cubed instead of squared. There's no m to speak of, and instead we got the lambda naught in there. So something's wrong, right? Well, it just means we have one last step, okay? What we have to do is we have to eliminate lambda naught from the equation and get m in there by taking what I call a total mass integral. It's a very similar idea, right? So it's a similar integral to the center of mass integral, because obviously you should see the parallel there. It's also a similar integral to the moment of inertia integral. It's just saying, okay, well, the total mass is just integrating all those little mass elements dm, all right? Again, that's just going to be as a constant if there was uniform density, but here there's not, right? Because I'm going to integrate from limits of 0 to L, lambda dx, but look, lambda is the function that I justified with the point-intercept method of finding the equation of a line. It's just lambda naught times, in parentheses, 1 plus x over L, okay? All right, so we just do this integral. Okay, it's a simpler integral because it's lower order on all the polynomials. So once we do the antiderivative, the 1 just becomes x. The x becomes x squared over 2, right, with the L, so over 2L. And then we got our limits, 0 to L. We evaluate those. All right, so then we just end up with L plus L squared over 2L. One of those cancel. And so then we're just going to have L plus 1/2 L, which is 3/2 L. So then we find that the total mass is equal to lambda naught times 3/2 L. Okay, and it would be a total mass, or the relationship between mass and lambda naught, and L for that matter, would be different if the distribution of mass was any different. Like say if it was getting 4 times denser at one end. Well, this would be a different relationship, okay? All right, but then we can go ahead and just solve for lambda, because then I'll be able to substitute it back in. All right, so then, or lambda naught that is. So lambda naught is going to be 2/3 m over L. And again, that was just by isolating lambda, because m is equal to that, see? Okay. And so then I would then substitute this back into the formula for the moment of inertia about the end. Let's do that. Thus, the moment of inertia about the end is going to be 2/3 times this here, which is just lambda naught, see? Okay, actually, it's this whole thing is lambda naught there. That's lambda naught, see? So 2/3 m over L replaces lambda naught. All right, we're able to cancel out that extra L, so now we have L squared. And then we've got an m, and we just have some coefficients. All right, so we'll just clean that up a little bit. 2/3 times 7/12 is 7/18 ml squared, and we're done. We've gotten the moment of inertia in the correct form. We've found it for this rod. What does it tell us, right? Well, first of all, 7/18 is bigger than 1/3, which means that this rod that gets denser at the end that's further away from the axis of rotation is bigger than a uniform density rod. That makes sense because there's more mass over here, right? It's denser at this end. If we consider an axis here like y prime and consider rotation about that axis, we'd actually get a smaller value than 1/3 because it'd be easier to rotate a rod where the denser part is closer to the axis of rotation. But here the denser part is further away from the axis of rotation, hence 7/18 being greater than 1/3 ml squared, right? Which is the uniform density rod about one end, okay? All right, let's compare it to other points. Let's find out about the center of mass, okay? So again, let's look at how it's worded. Right? What is the moment of inertia of this rod about an axis that passes through its center of mass? So I could start over. I could go back here. I could do different limits of regression. I could do negative L over 2 to L over 2, right? And I would actually have to also replace my lambda function because now my density function would have to match my new 0 point, okay? Because this density function here was based on lambda naught being at x equals 0, not x equals negative L over 2, right? So I'd have to have a different density function, but I could, and then I'd have to solve the integral with those new limits of integration, and that's fine. You could totally do that. But that'd be a lot of work, right? You know, at least a fair amount of work. Instead, we'll just use the parallax theorem because we already have the moment of inertia about the end, and we're asked for it about the center, so we're in great shape to use the parallax theorem. All right, so here we are. We're just going to use the parallax theorem. All we need to know is the distance from the far end to the center of mass, okay? And we know that the center of mass is 5/9 L. So we know that this distance right here is 5/9 L, right? But how do we know that? How do we know the center of mass? Well, we did it in a previous lecture. Now, I could do it again here, okay? But in lecture 27, where we actually showed how to calculate the center of mass for non-uniform density objects, if you recall, for a cone and for this exact rod, for a rod that's twice as dense at one end, right? We found that the center of mass of such a rod is 5/9 L. So I'm using that value. If you haven't seen lecture 27 or haven't seen it recently, go back and look at it because it's relevant techniques. And sometimes you have to calculate the center of mass for, say, a rod that has a different mass distribution, okay? So anyway, we're good to go. We'll just use our simple algebraic expression here. Since we're solving for the center of mass, notice I did some substitution. So basically I subtracted this term from both sides to get my center of mass by itself, right? Because I know it about some other axis, which happens to be the end. Okay, so then here's our expression. We're just going to combine like terms because these are, after all, like terms. And when we have 7/18 minus 5/9 squared, so in other words, 7/18 minus 25 over 81, then we get 13 over 162. And this is actually a fully reduced function. It doesn't reduce any more than that. 13 doesn't evenly divide into 162, no surprise. So here we have our moment of inertia about the center of mass of a rod that gets twice as dense at one end, okay? Great, that's interesting, I guess, right? You know, it's kind of a odd looking expression, but cool. But now let's look at a really interesting one. Now let's find, in part C, the moment of inertia of this rod about an axis that passes through its geometric center, okay? Well, its geometric center definitely isn't its center of mass, so instead it's a point that's L over 2, right? And so that means our H is going to be this little distance shown in the figure, okay? It's just going to be the distance between 5/9 L and 1/2 L, okay? Okay, so let's do that. So this is our H, see, 5/9 L minus 1/2 L, all right? Remember to square it because it's H squared, okay? And, right, and there's the L, I just factored it out. Okay, and we already know our center of mass, so now we're actually going to be finding about a new axis, an axis to its center. Plug everything in, all right, so we got our 13 over 162 ml squared. 5/9 minus 1/2 is 1/18. Remember to square it. And we get 1/12. Well, that looks familiar. That's because it's this. What? Is that right? Seems like right, but it is. It's the exact same as when the density was uniform. That's because it increased linearly. Even if it, say, got, you know, if we went from lambda naught to 5 lambda naught, we got 5 times as dense at one end. As long as it did it at a steady rate, as long as it was a linear increase between some density at one end and some other density at the far end, then when we do it about the geometric center, not the center of mass, but when we calculate the moment of inertia about the geometric center, we'll always get 1/12 for any linearly increasing density. I should say for any linearly increasing non-uniform density of a rod. So neat, right? All right, that'd be a fun one to prove, right? Okay, so let's do our last example, okay? So here, we're going to derive a moment of inertia again, but we're going to do it for a sphere, okay? So there's some extra things to pay attention to, but a lot of things that are similar to what we did for the rod, Okay, so to write the moment of inertia of a solid sphere with uniform density free to rotate about its center. So in part A, we're just going to be confirming what we'd find in the table of common moments of inertia, but make sure we can do it, proof of concept. And then part B, we're going to do it for a different density function, and one that actually has some decimals in it, right? Like a given density function, rather than having to define the density function by thinking about the equation of a line like we did in the previous example. All right, so let's get to it. So here is our sphere. So some things to consider, right? One way we're going to be conceptualizing the sphere of total mass m and total radius r is considering little spherical shell elements, okay? And each of those shell elements has mass dm, okay? So I want us to think about that. That's very similar to the rod. With the rod, we had little infinitesimal slices of the rod, right? But they were definitely one-dimensional because the rod didn't have any defined thickness to it, right? It was purely a 1D object. So here, our shells have a mass element, so that's similar to the rod, but they also have a shape, and that shape matters, right? The shape didn't matter for the rod, okay? So we're going to start with the same idea, the definition of moment of inertia, okay? That I equals the integral of r squared dm, okay? But in order to calculate the shape distribution of the mass, we need to consider that the moment of inertia of the sphere is actually integrating a bunch of moment inertias of shells. So here I've cheated and I've looked up the moment of inertia of a shell, which is 2/3 mr squared. Okay. Here though, m is replaced by dm because these are infinitesimally small shells, but the r squared is still there. So this 2/3 comes from a table, all right, from a table of moments of inertia for common objects, in this case, a spherical shell. Now you could actually derive that. We could use polar coordinates or spherical coordinates to do an extra step and derive the moment of inertia of a shell. But we need that because we need to care about the shape, right? If it was an ellipsoid instead of a sphere, it wouldn't be 2/3 mr squared, okay? So the shape absolutely matters and it has to show up. It didn't matter for the rod because the rod was functionally one-dimensional, okay? So it is an important extra step that we have to consider for other shapes. That would be true of a cylinder as well. We'd be integrating over hoops, but instead of just integrating in a sense that ignored the moment of inertia of a hoop. Okay. Now it happens that a hoop is mr squared, so it's a bit easier. But here the shape absolutely matters. It's 2/3 mr squared. Okay. Okay. But then everything from here is going to be a very similar process. We'll go ahead then and just plug in our 2/3, okay, mr squared, and then we're going to replace m with this. What the heck is that? Okay. Well, this right here, this 4 pi r squared times dr times rho, okay, this is dm. Why is that? Well, because it's surface area. The surface area of sphere is 4 pi r squared. The thickness is dr, and then the density is rho, all right? And that is volumetric density because the shell, even though it's infinitesimally thin, isn't 1D anymore. It's a full 3D object, so it has to be volumetric density. Okay? And volumetric density is just mass over volume. So it'd be mass over 4/3 mr squared. So this is fascinating, right? We've got the formula for the surface area of a sphere and the formula for the volume of a sphere both showing up, both relevant. Okay? But we can replace rho with this. It is a constant. It's going to come out of the integral. All right? So this we have, but first we'll cancel out some things, right? Pi is going to cancel. We'll have a 4 cancel as well. We have a 3 that's going to cancel here because this 3 is in the denominator of the denominator, which means it's effectively up here, which is why it cancels with those. Okay? And so then we can clean this up a little bit. We'll pull out anything that's a constant. M is a constant, so it comes right out. And R is also a constant as well. All right? Because that's the overall, just like L was a constant of the rod, here the overall radius of the sphere is a constant. Little r is not a constant because little r is the actual variable. All right, it's the variable that then we're going to be integrating across because dr is our infinitesimally thin thickness of our shells. So we're integrating over shells, right? We have all these nested shells, one after another, right? That's what we're integrating over. Okay, and we're going to have our limits be 0 to r, obviously. All right. One thing that's noteworthy here is we had an r squared, an r squared, and an r squared, which was an r to the 4th. That was it, right? And so then we have then r to the 5th once we do the rules of antiderivatives over 5. Okay. Excellent. And then we'll go ahead and evaluate the limits. Obviously, the lower limit is just going to be 0. When we evaluate the upper limit and clear up the fact that we have an r cubed here and r to the 5th, both once we evaluate it, both uppercase r's because it's the constant now, then we're just left with an r squared in the numerator. And there we go, 2/5 mr squared. Exactly what you look up in a table. And again, we did have to start with a known moment of inertia of a shell. That's because I didn't want to do the step with polar coordinates. Okay? All right. So that's great. We saw how it worked and saw some important differences and complications as compared to a rod. All right, well, what about when we have a different density function, because now we should be able to follow the same steps and be able to customize it to whatever density function we happen to have. So this density function is something that's denser at the center and becomes progressively less dense as we approach the surface. See, because that has that R over big R like relationship. So this actually is supposed to model the density of planet Earth, which has a dense core and then becomes progressively less dense as we approach the surface. Okay, this is a linear increase. That's not true. It's more like, you know, like defined demarcations in the case of an actual planet. But assuming that it kind of gradually becomes less dense, this would be our density function. Okay. All right. So same sort of steps. All right. The difference here though is that rho is not a constant anymore. We can't just say it's equal to m over v. Instead, we have to put in its function, which is a function of r. All right. But then it's all the same things. We just solve the integral. So we go through, okay, well, you know, I just basically distributed the r to the fourth, which gave me an r to the fifth term and an r to the sixth term. But that r to the sixth term is going to be over 6r, which means it will become a like term once we evaluate our limits. And then we're left with just this decimal. I cleaned everything up. Okay, but here's the thing. Are we done? No, because it's kind of like when we had the non-uniform density rod. We're left with something that is not the right form. We don't have some coefficient times mr squared. Big M isn't here at all. It's gone because you know, the density function didn't have it included. And instead of something multiplied by r squared, it's multiplied by r to the fifth. So we're not done. What do we need? A total mass integral. Yeah. All right. So same thing. We need to solve the total mass integral. So that's just going to be m dm. We'll just plug in that dm is just going to be equal to 4 pi r squared dr times rho. Okay, and again, I know that's not just the same as dx times lambda. Where's that 4 pi r squared come from? That's the surface area of the sphere, right? And each of those nested spheres has a different surface area, which is why r is a variable, because you know, they become progressively smaller. Their surface areas become smaller and smaller as you're integrating over them. Okay, but anyway, we did our substitution, and then we're just going to put in that rho is a function, right? So that's what I do. I replace rho with this function right here. All right, pull the dr out to the back so we can kind of make it look like a proper integral. Make it a definite integral from 0 to r, which we actually did in this step here. All right, once we did our substitution of our differential. And then we'll just go ahead and evaluate it. All right, so I distributed in the r squared, which means we have an r cubed over 3 term and an r to the fourth over 4r term. And then there we go. Then we find that the total mass, m, is equal to 4 pi times 1.83 r cubed. And we're using 3 significant figures here. Okay, so then I can then, what I'm going to do, I can say, okay, well, I guess I could substitute this in. I could say that r cubed is equal to big M divided by 4 pi 1.83, factor it on the r cubed. So, you know, this will just become r squared times r cubed. And I could just directly substitute it in. Instead, though, I'm just going to take a ratio. I'm going to say that the form of our non-uniform density sphere is going to be some coefficient beta times mr squared. Take a ratio of the moment of inertia of the sphere that we solved for divided by mr squared. All right. And then replace m with the numerical solution that I found, okay? And then, you know, the r's naturally, all the r's will cancel out in this case because we have an r to the fifth in the denominator and also an r to the fifth in the numerator. So then I find that beta is just 0.330. And that's kind of nice because that basically tells me, you know, like, how does this compare, right? How does this you know, distribution compare? Well, it's actually a little bit larger because 2/5 as a fraction, if you change it to a decimal, is actually smaller than 0.33. And that makes sense because, actually it's the other way around. This moment of inertia is less than a uniform density sphere. So this one is less than 2/5 because what we have here is we have that this one has more mass towards the center, which means it's actually easier to rotate because it's less dense at the surface, at the crust, right, if we're thinking of a planet. And then so our final answer, the moment of inertia of our non-uniform density sphere is 0.330 times mr squared. Okay? So hopefully you see how the steps come together. I know it is a lot of steps, but as long as you divide up those into individual steps, you can follow through and you can do any version of this problem. Okay? Well, thank you so much for watching this lecture video. I hope it was interesting and informative.